In this video, we're going to talk about nuclear magnetic resonance, specifically carbon-13. We're going to go over some examples of carbon-13 NMR and how you analyse them. This will also be followed by an exam-style questions video, which takes you through some specific examples of how you can be asked questions in the exam. So, uses of carbon-13 NMR. Okay. Well, first of all, before we do that, let's talk about the uses of NMR in total. So nuclei of atoms is done, and it can be done through hydrogen nuclei or through carbon-13. Now the hydrogen nuclei will be done in a further video, but in this one we'll talk about carbon-13. Now I didn't mention in the previous How NMR Works video about this low resolution. All low resolution means is the peaks you get will be single peaks. When it comes to a coupling, the peak splitting in hydrogen NMR or proton NMR, that will be explained later. It just means peaks split into multiples, but we'll go over that later. Now, carbon-13 NMR. You might be saying, well, why carbon-13, not carbon-12? Now, first of all, you can only see carbon-13, but at the same time, 1% of all carbon is carbon-13. So it doesn't matter. As long as you have enough molecules, you'll see plenty of atoms where carbon-13 is there instead of carbon-12, which means we can see the structure and the nuclei in many different molecules. Now the data obtained includes the number of nuclei and the environment the nuclei are in, but again, it makes more sense when we go through the examples. Just a reminder, the reference we use is tetramethylsilane, chemical shift to 0. Okay, remember all these carbons here are symmetrical all the way through, so therefore they all have the same signal, they're not in a different environment, okay, and they give therefore one sharp peak, as you can see here. And that sharp peak is removed when you do the NMR and set to 0, and then everything else is referenced from it, and it goes from right to left. Now the carbon environment. We're going to talk about a simple molecule of ethanoic acid to start off with. Now this will make sense as we go along, but let's talk about our exam tip. The signal for NMR will go further downfield at a higher ppm if the carbon we're looking at is bonded to an electronegative atom. Now that again will make sense, and we'll talk about it all the way through our examples, so don't worry if it doesn't quite work for you now. So let's look at the two different types of carbon that we have. We have a carbon surrounded by 3 hydrogens and bonded to another carbon, and then we have a carboxylic acid carbon. Now, you have a datasheet in front of you. Really important, there's a datasheet in front of you. Please use it throughout this entire video. Okay, so be looking at that. Now on your datasheet, there are ranges for different types of carbon you can see. And on the right hand side, you can see that carbon is bonded to carbon. You don't see any carbon-hydrogen types of carbon. So therefore, we cannot ignore this carbon-hydrogen and just look at this carbon bonded to another carbon here. So you can see CC is on the right. And that CC on the right has a range of 0 to 50. Then, if we look at this one, this is a C bonded to an O, or C double bond O. Now, the C double bond O has a higher ppm than the CO, so therefore it will go to the higher ppm of the two. Now that high ppm is 160 to 220. So I will get a CO at 160 to 220, and I will get a CC at somewhere between 0 and 50. Now, let's actually look at it on a spectrum. Now on that spectrum, you should see 2 carbon environments because you've got 2 different carbons. There's no symmetry down the molecule, okay? There's just 2 different types of carbon with different atoms all around them. So, if we put that up into the corner, and then we highlight them in red and orange. Now, and let's put our carbon-13 NMR in front of us. So we've got carbon-13 NMR, and as I said, it goes from right to left, so you've got 0 to 220 is your range, and that's your chemical shift. Downfield is towards the left end, and upfield is towards the right end. And the higher the ppm, the more downfield it is. Now, if it's connected to an electronegative atom, it's going to be in this direction. If it's not, it's going to be upfield. Now, you can see our C double bond O, okay, is between 160 to 220. So you can see that fits it because it's to the left-hand side of the spectrum, okay? And to the right is our CC because it's not bonded to an electronegative atom. So let's put our axis in and then put our peaks in. So you can see one peak, and you can see one peak at 190, and we got another peak at 50. So that tells us that we have 2 carbon environments, okay, and they're the same number of carbons each. We don't know how many carbons, we just know the same number of carbons each because the level of the line is exactly the same. And we'll discuss that in later examples. Okay, and we know that one's at 190 and one's at 50. And if you're ever going to do an exam, you have to say where you find the peak and in what range you find it. So I find a peak at 190, okay, and it is in the range of 160 to 220, and therefore it is a C double bond O. That's what you've got to state. I've got one at 50 ppm, which is in the range of 0 to 50, which is a C. And that would be proof, for example, that this at least should be ethanoic acid, but you might have to use other things to confirm that. Our next example is alanine. So this amino acid has 3 different types of carbon, so 1, 2, and 3. And you can see that the first carbon is bonded to a nitrogen. If you look at your data sheet at the time, you'll see that's one of your options, carbon bonded to nitrogen. And then our methyl here is bonded to a carbon. So we have a CN, we have a CC, and then we have a C double bond O. And you can look at your data sheet and hopefully you'll come up with these ranges that I've got here. 3 carbon environments and then 3 different ranges for your different types of carbon. Now let's look at what that would be like on a carbon-13 NMR. So, and then move that up. And there we go. And we've color-coded this hopefully to make it more simple, but remember in your exam it will just be black and white. So, we've got our chemical shift, we've got our downfield area, our upfield area, and we've got our spectrum x-axis essentially, and then there's our peaks coming out. We've got our red one, which is our C double bond O, coming out here, and then between this 160 and 220, and then we've got our orange one and our green one. You see the green one is slightly further downfield just because it's bonded to that electronegative element. That can really help in finding out which peaks mean which later on. So you can see that both roughly in the region of something of 0 to 70. So let's put the exact ones on. You've got the orange one at 50, which is in this region between 0 and 50 for CC, and the other one at 56, which is between 30 and 70. Notice they do overlap at times, okay? But it's really useful to get used to looking down this end because it's so indicative C double bond O's. And that means if you get C double bond O, you can start thinking, is it an aldehyde, is it a carboxylic acid, is it a ketone, okay, or maybe an acyl chloride. So these carbon NMRs may not tell you exactly the structure of a substance just on their own, but in conjunction with other things, they can give you the chemical shift of the chemical shift that allows you to get rid of some of the functional groups and focus on some others. Now, the last thing I want to mention is the fact that look at them, they're all the same level. That means they have the same number of carbon nuclei for each one. Now in this case, it's only 1 each, so 1 carbon nuclei and 1 and 1. Now we'll go through further examples that show you what happens when the level of this changes. But for now, this is your carbon NMR of alanine. Our next example is talking about the carbon environments of propane. You can see we've added a tip here, and it says look for symmetry. If you have carbons with the same environment, it will be only one signal. So if we look at propane, we can see that the CH3 at the end is next to a CH2. And they're both next to a CH2. And there's a plane of symmetry that goes right down the center. That means that those two carbons will have the same signal. The center one will have a slightly different signal, which means you only have 2 carbon environments, not 3. So that plane of symmetry is really important. Now that means we'll have between 0 and 50, 2 carbon-carbon signals, okay? And that 2 carbon-carbon signals will come out at the same ppm. Because they come out at the same ppm, we'll show you what effect that has. Okay, but first of all, let's put it up to the side. Okay, and then let's take those 2 signals we get. Remember, they're in the same environment. The green ones are in the same environment. And therefore, let's put a downfield and upfield on. Look at the size of that signal. So we've got 2 signals. Now there are 2 signals within that. There's one for this and one for this. And they come out exactly the same place. And because they come out exactly the same place, you have double the height of the peak. And this is a relative peak area. And when you come to proton NMRs that will be talked about a bit more. But this relative peak area means that you have twice the peak area for this one because you have 2 carbons for the same environment. So that gives us a hint when we're looking at carbon NMR to say, right, okay, if it's double the height of the other ones, and I know the other one is only 1 carbon, for example, I know this is 2. Okay, and again, let's just finish this off at the ppm. And you can see that the ppm, for those, if I was quoting this, I'd have to quote the ppm within the ranges. And I'd have to say that I have 2 carbon environments because the 2 carbon-carbon carbons, which are carbon-carbon bonds at the ends of the chain, are equivalent because of this symmetry. So in this example, we're looking at symmetry again. Remember, if carbons are in the same environment, it will only be one signal, and your relative peak area and peak height will be reflecting that. So we have cyclohexanol, and we've got a plane of symmetry that goes down the middle. That means the carbon at the bottom will give a signal, but these 2 carbons are equivalent, and these 2 carbons are equivalent, and then we've got the final carbon at the top. That means we only have 4 carbon environments. Okay, and they come out at these different ppms if you look at the data sheet. We just want you to look at the data sheet again. If that's the case, we can then put it onto a spectrum, and we can look at downfield and upfield again. And then we can see here's our orange one, which is our C bonded to C, which is at the bottom here. That's only 1 carbon, so we expect our purple one, which is our 2 carbons, to be double the height, and it's double the height. And it's getting closer to the electronegative element, so it's pushing downfield again. Then we've got the green one, double the height, again it's 2 carbons, and then the blue one coming out even further and much more downfield because it's closer to there, okay? So, if that's the case, you can see there, and you can use symmetry to find out which ones are equivalent carbons, and it gives you a bit more data about the molecule itself. We're now going to go on to look at benzene, and we've got trinitrobenzene here, and these are common examples in exams. So what you have to do is look at the symmetry again. You can see the symmetry going down here. You could fold it in half that way. There's symmetry going down there. You could fold it in half. In fact, the symmetry all the way through. Okay, this is a symmetrical molecule in total. So there's only 2 different types of carbon. There's a carbon that's connected to 2 carbons, and those carbons are connected to nitrogens, or there's the carbon connected to the nitrogen itself. So 2 carbon environments, okay, which will come out in the benzene area. So it's really important that you're used to the benzene area and look at your data sheet and know that that's roughly where it comes, because it will give you an indication as to whether benzene is around. Our next example is incredibly common, which is multiple substitutions of benzene. So we're going to list them in increasing downfield, as in, for example, higher ppm. So the lower they are down, the higher the ppm they are, the more downfield. Okay, so first of all, this has 6 different environments because there's no symmetry around there. Okay, so basically this carbon here and this carbon here are not the same because this is closer to that chlorine, for example, that is closer to that nitro. Okay, so we've got 6 different environments. If we look at those environments, we can see that this blue, red, and purple and green are further away from the electronegative elements, and then the really downfield ones are going to be the ones that are connected to the electronegative elements. Let's move on to the next one. So, next one, is there a plane of symmetry? Well, no, can't really fold that in 2, okay, at any point. Okay, so that means that all of them, if we move in that direction, all of them are going to have different environments again. Again, these 4 are going to be further away from the electronegative elements, so they'll come out first, and then the more downfield will be the ones connected to the OH and the Cl. So, last one. Think about symmetry here. Now, the symmetry here, you can kind of see a symmetry. I know that you've got an OH and Cl at the bottom, but you think about these 2 carbons here. These 2 carbons here have exactly the same environment. If you follow them up, they're exactly the same. Same as these 2. If you follow them down, exactly the same environment. Follow them up, exactly the same environment. So therefore, you can get that. So those will be the same signal. That will be the same signal. Okay, and then you'll get the 2 signals at the top and the bottom. If that is the case, you're going to get 4 carbon environments. Okay, and again, the green and the reds are going to be slightly further upfield, okay, and then this purple and grey is going to be the most downfield because they're connected to the electronegative element. Now, what you can see from here is a very, very common style of questioning, and they normally have this in an MCQ or something like that, where they'll say, how many different environments does this have? Okay, so it's really useful to get used to this style of question.